Cosa?
We talk in Spanish then.
Yeah, you can.
Okay.
You can, but I'm gonna talk in English.
Okay.
Or Italian, if you prefer.
Easier for me. Buenos días, bienvenidos a todos a este coloquio conjunto que organizamos todos los años entre el ICEMAD, la Universidad Carlos III, la Universidad Autónoma y la Universidad Complutense de Madrid, que ya se ha constituido casi en una tradición y que es una colaboración que nos ayuda a compartir no solamente experiencias, sino también ideas, diálogos, conferencias, y que es muy enriquecedora para todos nosotros. Quiero darles la bienvenida y presentarles a los que me acompañan en la mesa, que en primer lugar a mi izquierda está la profesora Eleanora Di Nezza de la Università, degli studi di Roma, degli studi de Roma, Tor Vergata, quien ha aceptado, y quiero agradecerle que haya aceptado darnos esta conferencia en esta ocasión tan especial para nuestros centros y nuestra universidad. Y a mi derecha está el profesor Iago Antonín, del Departamento de Álgebra, Geometría y Topología de nuestra facultad, que es el organizador de este evento y el organizador por parte de la Universidad Complutense del coloquio conjunto. Muchas gracias por participar también. Y simplemente pues agradecer a todas las instituciones y a todos los que han participado en la elaboración de este acto, pues su colaboración, y en especial a Iago. Con que a continuación le voy a pasar la palabra a Iago Antonín, que nos va a hacer una introducción mucho más detallada del perfil profesional de nuestra invitada. Cuando quieras, Iago.
Muchas gracias, Antonio. Buenos días a todos. En primer lugar, presentarme y decir que desde este año soy el organizador del coloquio por la parte de la Complutense, y que este trabajo lo ha estado haciendo hasta ahora Pierluigi Tempesta, y le agradezco tantos años trabajando en esto. Y bueno, de cara al año que viene, si tenéis sugerencias para ponentes o para este coloquio, pues podéis contactar conmigo. Y bueno, por la conferencia que nos trae aquí, es un placer contar con la profesora Di Nezza, que es una matemática excepcional en el campo de la geometría compleja. Actualmente, como ha dicho Antonio, es catedrática en la Universidad Tor Vergata de Roma, pero ha tenido un impresionante periplo por Francia. Ha tenido puestos en la Sorbona, en la École Polytechnique y en la Escuela Normal Superior de París. Su investigación está en el área de la geometría compleja y el análisis, como he dicho, en especial en la geometría de Kähler, que es el tema de esta conferencia. Y bueno, pues su trayectoria está plagada de reconocimientos. Tengo aquí anotado que en 2021 fue galardonada con la medalla de bronce del CNRS. En 2023 obtuvo el premio Reine Elisabeth de la Academia de Ciencias de Francia. En 2023 también el premio Bartolozzi de la Unión Matemática Italiana. Y además su trabajo ha estado financiado por la European Research Council con una starting grant, y ahora disfruta. Consolidator. Ahora con una
I do understand.
Y bueno, pues dicho todo esto, creo que su currículum habla perfectamente de su capacidad, y el título de la conferencia de hoy es Special Metrics in Kähler Geometry. Y por mi parte nada más, le damos la palabra a Eleanora.
Thanks a lot. Okay. Thanks a lot for the introduction. I mean, I feel a little bit shy in this occasion, even if I'm not. But anyway, now it's time for maths business. I'm sorry, I cannot still speak in Spanish. My Spanish is very poor. I can just say cosita, basito, and whatever, all the small things. So let me do that in English. As Iago said, I work in Kähler geometry. Maybe some of you doesn't know what this means, so I'm going to introduce the setting, give you examples that you can keep in mind for the rest of the talks, and hopefully give you ideas, okay? So this is what I want to do. So the setting is the following. We are going to work on a smooth manifold, and in particular on a compact Kähler manifold. Don't be scared, this is just a name at this point. So when I say compact, I mean that I have no boundary issues, and manifold, it means that I'm working with a smooth object, a smooth complex manifold. So this guy here is a smooth complex manifold. Complex manifold means that the charts are bilomorphic to domain in Cn, and as I say Cn, so I decide that I denote small n the dimension of X. So the complex dimension is n, and here this little omega is the extra structure that I have when I work with a Kähler manifold. So a Kähler manifold is a pair of a smooth object with an extra metric structure, and this is given by this omega, that is a smooth form, a smooth differential form. So to be more precise, a 1-1 form with a lot of properties. So it's real, namely when you take the conjugate, it's just itself. Then it's closed, meaning that the d of omega, the differential is 0. And this is in particular, it tells me when I have something d closed, it gives you a cohomology class, whatever it means, but this is an object in the cohomology. Real coefficient, because the form is real. So this and this and this. And finally, I want my form to be positive. So what all this means, I'm going to write in coordinates, because coordinates is going to let you at least understand what's the shape of this guy or this object. So in coordinates, locally, so you choose, I don't know, the ball, the unit ball, is going to be square root of -1, or I. It's going to be in the following, the unitary, the imaginary part. Sum over alpha and beta, some coefficient, d, and then d zeta alpha wedge d zeta beta bar. Okay? And so this is what I mean, a 1-1 form. I mean exactly that I have some combination for some coefficient, and then I have this, the canonical 1-1 form. And this coefficient here, the g alpha beta beta bar, are actually alpha and beta, are the entries of n times n, where m was the dimension, of an Hermitian metric, like in algebra, in Hermitian matrix. And the fact that the matrix is Hermitian is actually because the form is real. So this thing, they're going to talk to each other. And it is positive definite, as the positive definite as for a matrix. And this is actually equivalent to us that the form is positive. Okay? So maybe if you're not familiar with all these notions, you can think at something that writes like this, and it's going to be perfectly fine for the rest of the talk. But also, let me give you some examples that you keep in mind, okay? So I'm going to give you actually 3 classes of examples. So examples. So the first one is my, let's say, maybe our favorite, the complex projective space, CPN, complex projective space. So what is that? This is just I take Cn plus 1, then I remove the 0, 0, 0, 0, and then I quotient, sorry, this is equal. By a quotient by the relation say that lambda, that Z is equivalent to W if and only if there exists a non-zero lambda such that Z is equal to lambda W. So they are on the same complex line. Okay, so this is a quotient, and this is an equivalence relation. Okay, CPN, maybe I can write you a picture in dimension 1. This is also a good thing. CPN is the complex CP1. Actually, CP1 is bilomorphic to the sphere, the Riemann sphere. So the picture is really this. So this is one example of a Kähler manifold in dimension 1. First example. So then I say three examples. The second one is the torus. So it's Cn, and then I quotient by a lattice in here. And again, let me draw the picture for dimension 1. This is just C over a lattice, and this is the donut. Okay? So this is the second class of examples. And the third one is when I take X, that is actually can be the zero locus of some homogeneous polynomial defined on Cpn. Okay? So let me take Cpn, so it's going to be P equal to 0, so P of Z equal to 0, where this one is an homogeneous polynomial, and Z is in Cpn plus 1. Why Cpn plus 1? So that my manifold here is going to have dimension 1, right? Because it's given by, is another surface, it's given by one equation. So m plus 1 minus 1, it gives me n. Okay? And in dimension 1, once again, if I choose correctly my, I didn't say degree of degree, d positive d, okay? Any degree you can choose. And if I choose my degree correctly, then examples of this are, for example, object surfaces with 2 holes. Or, I mean, I say 2, but it can be more, right? So these are all objects, all these objects are Kähler manifolds. So these are really objects that you can think about when I'm going to tell you all this story. Okay? And the problem I want to talk to you about is actually a classical problem in Kähler geometry, but even more in geometry in general, whatever geometry you want. If you want algebraic geometry, differential geometry, you just change your object and your special structure you look at. The problem is to find special metrics, as the title of my talk says, special metrics on a given Kähler manifold. And when I say in a given Kähler manifold, since I told you that the Kähler manifold, it comes with a Kähler structure, the omega, the reference one, I want special matrix that belongs in the same cohomology class of omega, the reference form. This is the reference, the one that we start with, reference form. Okay? So I want to look for omega tilde, let's say, in this class. And maybe you don't know, you're not familiar, you don't feel comfortable with cohomology classes, but then I can tell you what the first magic of the Kähler word, and that is going to actually make this problem and this expression simpler. So let me look it up, let me tell you. So first magic of the Kähler word, and this is also why I do like it a lot, is that I mean, the first magic is a theorem that is called the Dedebar lemma that holds on Kähler manifold, and it says that every Kähler form omega tilde in the same cohomology class of omega can be written as omega tilde equal to omega plus I dd bar of phi, where this phi here, for some phi, that is a real valued smooth function. Smooth function. So any Kähler form, any object in here, any Kähler object in here, it writes like this when this one is fixed. Okay, and this one can move. It's like the perturbation. And then when I write dd bar, I mean this. I mean the holomorphic and anti-holomorphic derivatives. Let me say like this. So this is the sum over alpha and beta. Yeah, because of the two derivatives. So the Hessian of the complex Hessian of phi here, dz alpha, dz beta bar. These are the coefficients. And here I have dz alpha wedge d zeta beta bar. Okay, this is just an object. We can really let it down on whatever it is. But then why I told you so? Well, because thanks to this first magic lemma, we can actually, instead of find the special metrics, so there are forms, we can look for special potential, special functions, because this is what we need to look at. Okay? So instead of finding special metrics, I mean, it is equivalent, thanks to this lemma, to find special potentials. So we can work with functions. When I say potential, is a function, okay? Okay, and then, so this is why I'm going to introduce this space. That's going to be the space of Kähler potentials. This beautiful H is the set of all smooth function, real valued, because everything has to be real at the end of the day, such that when I do omega plus I d bar of phi, I have to get a Kähler metric. So this has to be positive. Okay? So this is my space, so beautiful H. So think about beautiful H, whatever it is, in words, this is the space of Kähler potentials. Beautiful H for Kähler potentials. I'm going to tell you this. So this is what the aim of the game. Let me use this. Maybe I can go in here. Very good. So the first thing that I'm going to tell is that this space is an open, so not all contained, an open convex subset of the real value smooth function. That it's open because this condition is open, the strict positivity is open, and that it's convex. You can play and you can do a convex combination. You can do phi over 2 plus psi over 2, and this is still going to be a Kähler form. So open and convex of this guy. Very good. But, and this is like the warning I need to tell you. I'm going to write it here. You tell me if you don't write. H as, I mean, since it's an open convex set of the C infinity function, has infinite dimension. When you put, for example, the Frechet norm of this space. Infinite dimension. And this is going to cause a lot of problems, and we're going to see them. So anyway, we have this space, and we understood what's the aim. The goal is to find, we said, special potentials in H. Okay, very good. So what does it mean to be special? In Kähler geometry, special, I mean, in general, in geometry, special can mean that, for example, a part of the curvature of this guy, of the new guy that we want, is constant. But we do have a lot of curvature in any dimension n, so special potential can mean several things, and I can start you, like, there are different levels of difficulty. So we can ask for phi such that omega plus I d bar of phi is Kähler-Einstein, is a Kähler-Einstein metric. So I'm sure that you heard about the Einstein equation. So the Kähler-Einstein equation is actually the Kähler analog in the Kähler world. So we ask the metric to be Kähler, we ask the metric to be Kähler, so to be in H, and the Ricci curvature of this guy, that I'm going to call omega phi, to shorten up, to be proportional to itself. Okay? And lambda is real. So this is really the Einstein equation in Riemannian geometry will write exactly like that, but the metric has to be only Riemannian in Riemannian geometry. And the Kähler word, we force it to be Kähler. So this is the first equation. And the story is very long. It starts in the 70s, and there have been contribution of geometers like from the 70s until 2014. Okay, so there is a long story beyond the resolution of this problem. Then the next in line, more difficult notion to look at is the potential, the special potential phi, when the special potential phi is asked to have scalar curvature. So instead of Ricci, we go up. So the scalar curvature of omega phi, it has to be constant. So this is the scalar curvature. It's another part of the curvature. It's the trace of the Ricci, actually, curvature. Okay, and why I say that I go up in difficulty, so now I don't want to, I mean, I can write the equation if you want, but what you should keep in mind is that this is a second order equation. Actually, it's a system of equation, and this is fourth order. So this is why I say I go up in the difficulty, okay? And when I say equation, it's a nonlinear equation, okay? So really, it's like, it's a mess. Okay, very good. So, and then I could go further. I could talk about, so these are called CSCK metric. So CSCK for constant, scalar, curvature, Kähler metric. So the last K is for Kähler. Because once again, one could talk and one could ask about constant scalar curvature metric in Riemannian geometry. And I could go further. I could talk about extremal metric, whatever it means right now, Kähler-Ricci-Soliton, and so far, so on. There are really like a lot of possibilities. Let's say that we start with this one, that it's the easiest. If it doesn't exist, we go on the next level, but it's more difficult. If it doesn't exist, we go to the next level, but even more difficult, and so far, so on. Okay? But all of this, finding the special potential, goes back to understand the geometry and the properties of this space. Okay? So let me write it down. I'm going to go in here. So goal, understand the geometry of H. Okay, very good. But once again, why do we want to do that? Well, because one approach, one strategy to try to solve this problem, so why? Because one strategy to kind of solve this problem rely on the so-called variational approach. Variational approach. And what does it mean? Okay, here is the idea, and this is what the idea that I wanna pass to you. So we consider a functional, let me say M actually is for Mabuchi, defined on beautiful H, and it goes to R. So this M, it takes a function, and it gives you a real number, M of phi. This is the Mabuchi functional. And how this functional is defined, I mean, all the time, for any equation, for any special metric that I choose, let me focus here on the second one, for example, because the state of the art is kind of nice up to here. So the Mabuchi functional is defined in an implicit way, so that the critical points are the metric I'm looking at. Defined so that, let me write it down, so that critical points are the CSCK metric. So what does it mean in math? It means when I take the Mabuchi function on a perturbation of what it should be the CSCK metric, and then I do the derivative, and then I evaluate 0. Then I get 0 if and only if, when I get 0, I get the phi is CSCK. So this is how really one can define this functional like this, but then the problem is this is not explicit at all. Does it exist, this functional? Can we really look at the primitive? And already this is the second magic. The answer is yes. M of phi, M, as an explicit expression, that I'm not going to write it down for you, but what you should know is that it's going to be divided by two parts that are going to play, sometimes together, sometimes against each other. And one part is the energy, and one part is the entropy. And if you know what is the entropy of a measure, it's a good thing. It's the same entropy. Anyway, energy and entropy. Entropy. Okay, very good. So what's the game? We have this functional. At the end of the day, we have this functional defined on H that gives me real value, and I want to understand, thanks to the way it was defined, I want to understand the critical point. Want to understand if there exist critical points. Very good. And the theorem goes like this. I can write it down here. So the theorem goes like this. And this is a theorem due to Chen and Cheng in its latest version in 2021, and this was really a big breakthrough in Kähler geometry. After that, they were like, woo! And there are some nice ideas in this. And the theorem says, well, there exists a CSCK metric, namely a critical point, if and only if M is proper. So the functional is proper. And I'm going to be more precise on what proper means, but the picture you should have in mind is that you have a functional of this shape. Proper means that you have the asymptotic. And then if you have the right asymptotic, there exists a minimum, a critical point. Okay, but now we relax. And I'm going to tell you, and this is the idea, why a theorem like this should be true. Because I told you that this H is infinite dimensional, we don't understand this structure, there are a lot of things that could go wrong. So why a theorem like this is true, and what do we need to prove it? Yes? Say it again? So if you take x to CPN, so something I didn't say, I said first in line Kähler-Einstein, second in line CSCK. When the cohomology class of omega is the first chain class of the manifold, then actually CSCK metrics are Kähler-Einstein. And on CPN, the Kähler-Einstein metric is the Fubini studi metric. So you solve it. In CPN, the Kähler-Einstein metric is the Fubini studi. So it's a very, let's say, famous one, known one. And the Ricci of that, the lambda is positive. So it would correspond to this case of the sphere in dimension 1 with positive Gaussian curvature. Does this answer to your question? So the theorem, the inspiration, goes back on the finite dimensional inspiration. The finite dimensional case theorem, it says, well, I get a functional from Rn to R, strictly convex. Then there exists a unique minimum point, if and only if f is proper. And what does it mean proper? Here I can say if and only if there exists two constants such that f of x is bigger or equal than A times X, the absolute values of X minus B, for any X in Rn. Okay? So this is maybe we are going back in analysis 1, and maybe this is something that if I write it down, you're not scared, you feel a little bit more comfortable. But what we're going to do is that we're going to reprove this theorem. We go back to the basic, and we're going to see what we need, what kind of structure and what kind of techniques we do use to what kind of facts, more than a technique, we use to prove this theorem. Okay? And then we try to go to the infinite dimensional case. Okay. Let's try this game. Here it is. Very good. I mean, and when I write this theorem, the picture is exactly the same, right? So the function goes like this, and then you have a minimum. And also, maybe let me say that the strict convexity is associated to the uniqueness. But for the moment, we only care about existence, right? Okay, let's go. So I do first prove this arrow. So f is proper, then there exists a minimum. Okay, let's go. Okay, I take xj, minimizing sequence. So what does it mean? By definition, it means that the lim inf over j of f of xj is equal to the infimum of a Rn, and I want to prove that this infimum exists, right? I mean, the infimum is taken over an x0. Very good, so this is definition. And then by properness, that is my assumption, by properness, we do know that, so first of all, I take, the first thing is that since fxj goes to the infimum, if I take j very, very large, then f of 0 is bigger than f of xj, right? Because f of xj goes to the infimum. So this is because xj is minimizing. And then I use the properness in here. And this is bigger or equal than a times xj minus b, where a and b in here, and this is the power of this properness condition, is that this a and b does not depend on the value, on the point. Okay, so what does it tell me? Look at this, that xj is less or equal than f of 0 plus b divided by a. But what does it mean? It means that xj is bounded. Xj is a bounded sequence, and so since we are in Rn, and Rn is complete, then we know that up to extract a subsequence, this sequence is going to converge to something. So here we use, so this is what I emphasize, completeness. And here it is, completeness. Xj, let me say that xj, but it should be the subsequence, converge to to something that I call x naught, right? But then we know that f is convex and continuous, right? And this means that the limit, if you want, that f of j is f evaluated at x naught, right? But this guy was the infimum by definition of minimizing sequence. So we just proved that x naught is the minimum point. Minimum. UP, that's done. And I also wanna let you observe something. This is important when we want to generalize. We wanna use the minimum of the things, right? So that here, if I would have had just an inequality, the same argument would have worked, right? Because the infimum bigger or equal than f, it means that this guy has to be the minimum value, right? So actually, we don't need just the continuity, but we need lower semi-continuous. Lower semi-continuous, it means exactly this. Okay? So this, we need the function to be just lower semi-continuous. Very good. This is one direction. And now on the other blackboard, I'm going to prove the other direction. Here it is. So this is the other direction. It goes like this. So now we know that there exists a minimum point. There exists x naught minimum. And first of all, I look at the maximum over the sphere. So dimension m, the sphere in Rn, so it has dimension m minus 1. The sphere centered at x naught and of radius 1. So this is x naught, and I take the sphere. So all the point in here has distance 1 from x naught. And then I look at this guy. Let me say x minus fx in naught. And this is equal, so this maximum, since the sphere is compact, is attained to at some y, right? There exists a point in the sphere, y in the sphere, such that this is equal to f of y minus fx naught. Very good. So here we use completeness of the sphere. Compactness of the sphere. Very good. This is the thing. And then I call this difference here, I call it A. And this A is strictly positive because y is on the sphere, so y cannot be equal to x naught, and the function is strictly convex. Okay? So what does it tell? We are finished. So now if we look at this ratio, x naught. Now this ratio, because the functional again is convex, so this ratio is increasing in both variables, so increasing in x. This is bigger or equal than the max over Sn minus 1 of the same thing. But this guy is equal to 1 because we are on the sphere. So the length between points is just 1. And this guy, we say that is equal to A, positive. Okay? So what does it tell? I'm going to write it here. It's going to tell me that f of x is bigger or equal than A times x minus x naught plus f of x0. And then, I mean, I can do it. You use the inverse triangle inequality. This is A of absolute values of x minus A absolute values of x naught plus f of x0. And then you can put all the minus here. You can put a plus. You take the absolute values, whatever. And this is going to be my B. And this is exactly the properness. So, and this B here, so this A and this B does not depend on x, depend on x naught, but x naught is fixed. Okay? This does prove my the theorem, both directions. So we're here, f convex. So let me put it here, the conclusion. Let's try to catch up what's going on and what we need to try to prove a theorem, the Chen and Chang theory. So what we need in this theorem is, so we said in order, if we go there, we say completeness. So in completeness of Rn, if we stick to the finite dimension, the completeness of Rn, then we use it the lower semi-continuity of the functional of f. Then we use it the convexity of f along segments, and then we use the compactness of the sphere. So of a subspace of this Rn, right? Very good. And now we start to have problems, because what's our picture? Our picture is that, so first of all, M, the functional that we want to study, is defined in this infinite dimensional space. It gives me real values, but the first question is, H should be complete with respect to what? What's the metric on this? How we do measure the distance between two Kähler potentials? So H complete with respect to what? To what? And second thing, that it's more a bad news. is that H is not convex along segments of the type 1 minus t, 1 element plus t phi 1, right? These are the segments in that space. So we started with a question, like a kind of a deep one, and also bad news. So how to get rid of all of this? Well, here's the thing, and this is the good news, but that required the work of many, many mathematicians. So let me say the good news of facts is that there exists a family of distances, let me call dp, where p is bigger or equal than 1 on H. So this is the first fact. And this means, at the end of the day, the H endowed with this distance is a metric space. Metric space. And this is already not trivial at all, and I should mention my friends and collaborator, Tamas Darbas, that proved, let's say, the final version of this in 2017, so not long ago. Okay, first thing. Second thing, that actually there is a way, this is what I'm, the course that I'm giving is in math. Yes, there are some properties I'm going to tell you something about. There exists a notion of geodesic, the geodesic between 2 points in H, 2 Kähler potential, very good, and these geodesics, and these are these minimize the distance. So the distance, this dp, is going to be minimized by some special path that I call geodesics. There is a way to define them. But, and here it's a big but, these geodesics are not smooth. They leave the space of Kähler potentials. So they are just C11. No, even better. Okay? So they leave the space. So what does it mean? If already the geodesic leave the space, it means that my H cannot be complete. Because there is already something that should be inside that is outside. So H, with respect to this dp, is not complete. So this is a bad news, right? This is a bad news because I told you that for the proof we need completeness, okay? And this is why one has to look at the completion of this space. And not only one can do, because of course we can look at the completion. We have a metric space, we look at the completion. But we also understand what this completion is. And this is something, this guy here, it's a larger space. So H is strictly contained in a P. And this is a finite energy class. It's an energy class, like Sobolev spaces, if you're more familiar with those. But the point that I want to stress is that smooth functions belongs in here, but there are also singular stuff that belongs in here, alpha small, sufficiently small, okay? So this is just an example. The point that I want to make, and this space is much larger than this, okay? And this means that we want to do all the arguments that we did. We need to deal with singular guys. So anyway, but now by definition, this space is complete. And also good news, geodesics are inside this space. Geodesics are in this space EP. So EP is a geodesic metric space. This we like even better. And now the last news the last news, and then I can finally tell you the final. This is a good news in here. Very good. And the other good news, or a fact, so 3, is that M, the Mabuchi functional, is convex. It's not convex along segments, but these are not the right things to look at. It's convex along geodesics, because segments were geodesics in Rn. It's convex along geodesics, the singular objects. And this was proved by Berman and Berson in 2017, 16, 2016. And final news is that M can be extended on EP. So because M was defined on H, right, the beautiful H for smooth guys. And what I'm saying is that we can extend for singular ones. So can be extended in a lower semi-continuous way with respect to dp. It's not better. Okay? Because of course, when I say a functional, continuous, lower semi-continuous, it respects the topology that we choose, right? Here is the topology is given by the metric, and the metric is dp. Good. So, conclusion. Let's wrap it up. Conclusion. And the conclusion, I am going to write the conclusion for p equal to 1. And there are 2 reasons why to fix p equal to 1 in this family. So the first one is because E1 is the larger space. So if we prove a theorem, it's easier to prove a theorem on a larger space. And the second reason is because E1, the space is 1, is really like very linked with the energy functional, the energy part that appeared in my Mabuchi functional. I said that the Mabuchi was energy plus entropy, and this energy part is really linked with this E1, okay? So the conclusion is this one, is that I have M, the Mabuchi functional, defined on E1 with respect to lower semi-continuous with respect to D1. It gives me real values, but it can also go to plus infinity, because I have singular stuff. And this guy is lower semi-continuous, convex along geodesics, and this space here is complete. Good. And maybe the last fact, that is going to be my 5. Let me say, I'm going to write the 5 here, sorry. Is that, you remember, it's still there. So in the final dimensional case, we use completeness. Now we have it. We use lower semi-continuity. We have it. We use convexity of the functional. We have it. And we use that something is compact. Here, this something that is compact is the sub-level set. The sub-level set of the energy functional. Those are compact. Okay, and this was proved by Berman, Buxom, so the French school. This is how Buxom, Essidieu, Gagezerier. And this is more 2013, something like that. Anyway, kind of new. Okay, so we have all the ingredients, and do I have it? Do I have it? No, I erase it. It's okay. We have all the ingredients, and then the theorem, using exactly the same arguments that we proved for the final dimensional case. The theorem is there exists a phi in E1, minimum point, critical point for the Mabuchi functional, if and only if M is proper, meaning that there exist A and B such that the Mabuchi is bigger or equal than A times the distance between 0 and phi. This corresponds to the absolute values of x, minus B. And this should hold for any phi in E1. So after all the facts that I mentioned to you, you can really use the same exact arguments that I gave in the finite dimensional setting to prove such a theorem. What's the catch? That here I just proved that there exists a critical point in E1. But I told you that E1 can emit singular stuff. It's much bigger than H. And what we wanted at the beginning, it was a metric, so something smooth. So problem, phi a priori lives here. And in order to prove that phi actually belongs to H, so the minimum belongs to H, it is done using uniform estimates and the continuity method. And this was somehow a huge work that Chen and Cheng did it to complete the picture. Okay, very good. So this is the story, let's say state of the art, how my contribution goes. So I'm going to finish up and tell you so as you can see, all of this is very new, right? So I told you that the theorem, this last theorem is 2021. And then let's say that all this story that I told you about started in the 80s, but at a kick in 2005, something like that. And then so in 20 years, they were like many Kähler geometry, really working harder, fighting sometimes to prove such a thing. So me, how did I go, in which direction I studied? So I did look at the cases, what I call the singular setting. So when the manifold that we start with, it's not a manifold, it's not a smooth thing, but can have singularities. So something like that, okay? Or something like that, con singularities. And this actually comes up to study, to have new techniques to study the problem when the form is not positive but have some degeneracy locus. So it's 0 somewhere. Very good. And one has to define again this metric. He has to define geodesics. He has to deal with singularity. And this is why the situation is much more complicated, let's say. But then at the end of the day, all goes well. So in this concern, I'm just gonna mention some results of mine with some collaborators if you wanna have a look. So in this concern, I should mention work in collaboration with Gedge, and then with Lou, with like a series of paper with Darvash and Chin Lu. So here we are talking at the year 2020, 2020 something, 20 now, why not? So this is one direction. And in the other direction was also what I did is to go to the next level of metrics. So here we are at the second level, CSCK, right? So next level of metric. On metrics. And so what I did in collaboration with my postdocs, Simon Joubert and Abdelal Adili, and this is really like something much more recent in a series of papers, is to look at what we call, actually it's a new geometric notion defined by Abdelal Adili, look for what we call weighted CSCK metric. Weighted CSCK metric, but this, I mean, we call weighted CSCK metrics because there are weights, a function that comes into the picture. So if you want, it's going to be the weighted scalar curvature of the metric is equal to another weight. So these V and W are functions that I call weight. But I mean, it's not just a merely generalization of CSCK. really this equation here, depending on the choice and the symmetry that we put, is gonna unify all the geometric notions that are known. So what I mentioned, extremal, Kähler-Ricci solitons, these are all contained in here, okay? So this is why we wanted a theorem, a very nice statement for all these metrics, hence for several geometric notions, without reproving case by case. And the theorem we have states like this, and then I think I can stop. So the theorem, it says, once again, there exists a weighted CSCK if and only if another functional that I call the weighted Mabuchi, that of course has some similarities, but much more intricate, is proper, once again. And so this is the statement, even I can get more precise, but this is the kind of statement what we have, and the idea is always the same, but the difficulty, like really the technicalities, increases in exponential ways, also because we do have to take care of all these weight function coming into the picture. And a priori what we did in here, what our contribution were these a priori estimates once again. Okay, I think I can stop here. I really thank you for your attention.
Okay, thank you, Eleanora, for this. Thank you, Eleanora, for this talk. It was very, very nice. I don't know if there is any questions in the audience. I have some questions, but okay, let's go first.
So after chain and the solution of the Kähler problem by donation chains, what do you think are the main challenges in the field now?
So there is this thing that I didn't say, and this is when I say Kähler-Einstein, and I say there were like a lot of work that went for 50 years and whatever. The final statement for Kähler-Einstein is there exists a Kähler-Einstein if and only if there is a functional, it's not Mabuchi, it's simpler, it's called ding. The ding functional is proper if and only if the manifold is k-stable. So there is this thing about the metric structure, a property, more analytic property, this functional being proper, and an algebraic geometric stability. So there is the link between these three words, let's say. So for the CSCK case, so the Chen and Chang gives you the first equivalence. So there exists a CSCK if and only if the Mabuchi is proper. And then there is this result by, I guess it's pretty new, by Buxom and Johnson, that actually gives you also the algebraic geometric version of it. So they introduce a new version of stability, the right one, let's say, because we have to adapt. And they have all these things. And what I didn't say is that, I mean, there were my contribution and many other more. So this picture is settled up also in the singular case. So for singular manifold, we can play the same. While defining the object, we can have the same kind of statements. So this is for the CSCK word. And then the main challenging, I mean, let's say that people are trying to understand if there is a general setting. This is also goes in the way of my work, right? And a general setting where we can prove a theorem without going case by case, right? But then it becomes more difficult. We are trying to do. Then I don't know if it's a main challenge because somehow the techniques are there. And the ideas are there right now, but then I don't know. I don't know that if we need just to be patient and to really work it hard, or we need some new ideas to complete the picture. But let's say that in this direction of special metrics, we are doing pretty good.
More questions?
This space has been instrumental for the whole thing.
This E1?
And the
yeah.
dual and the dual. But if you study it by itself, you already have geodesics, and you will have also geometry in some way. I understand from some conversation.
So,
That geometry is not very clear, or at least only formal.
but the geometry of what? Of this?
H.
Of H. So what you would like to know about H?
No, I don't. I would like only to know.
So something that I can tell you,
You have geodesics defined there, so you could have.
But they leave the space, the geodesics. They leave the space. So what I can tell you that maybe it's very nice is that that H, this is something that I told you, but I didn't write it down. When I look at the distance for p equal to 2, so p equal to 2 is a very special case because all this family of distance for any p, they come from a Fiesler structure, from a norm. P equal to 2 comes from a scalar product, like the Hilbert spaces. So it's much better. And we say that this space is not complete, but then we can look at the completeness, and this space is K0. K0 means that, if you want, if everything would have been smooth, it means that the sectional curvature is negative. Negative sectional curvature. Sectional curvature. And this is also, let's say, the reason, the inspiration why we get, I didn't tell you, but we get the geodesics are unique. And not only are unique, but also they are the same for all the distances. This is one other magic of this world. Yes, it's magic. And when you see it, it's like, really? But yes. So the geodesics are the same, and in this special case, this Hilbert case, let's say, the curvature is negative, and this is why we get uniqueness. So we do know, so this is related to the geometry of the space, right? I would say. But this is not true in the space. Yeah, I can tell you also this. In the space of dp, for any all the dp, this is, it cannot be K0 because of these Hilbert properties or whatever, but this has been studied, this Boosman convex, namely that the distance is convex as well. So you have this kind of property of negativity in some sense. So this is a notion in geometric measure theory, in metric, for metric spaces, notion for metric spaces. So this space, this H, is really been studied in the pluripotential way when I talk about these energy classes, also from seeing it as a metric space as well. So we do have a pretty good understanding of what we would like to know. I don't know what you would like to know. Think about it. We still have 1 week to figure it out.
So thank you very much for the great talk. Actually, now it seems like this very complex field seems to be quite easy, which is so thank you very much. Just a question, is there a way of formulating this minimizing as a geometric flow, like in the Ricci flow? And you can understand
yes.
that this, when you go out of H, is like you are blowing up your solution or having this bubbling or whatever?
So let's start from the Kähler-Einstein case. In the Kähler-Einstein case, there is the Kähler-Ricci flow. So what I told you, behind there is an elliptic story. So there is an equation, an elliptic equation coming into the picture. You can also think of this in a parabolic way. So there is a flow called the Kähler-Ricci flow. Let me call it omega t, that is going to satisfy the Ricci flow equation, but in the Kähler world. So asking that the metric remains Kähler, and it's Ricci of omega t with some initial data. And what is known is that if there exists a Kähler-Einstein metric, this flow is going to reach it. So this is another way to get this metric. In the CSCK world and in the weighted world is a bit more complicated. But so this is, for example, in a work in progress with my 2 collaborators there. So there is a parabolic version, but of course then the techniques are a little bit different. There are different quantities that you have to care about, and some of them, for example, I mentioned this entropy thing, right? This entropy thing in this weighted world is also related to the Perelman entropy someone knows about. Okay, so I mean, it's complicated, but why not? So we're trying.
Thank you.
He was waiting.
So maybe somewhat related question, just in case another generalization could be, say we have an extra data, a bundle fibering over our Kähler manifold, and we want to study a couple problem for, say, a connection and the metric downstairs. Are these techniques somewhat applicable or easy to generalize to that sort of situation?
I don't know yet. We are trying. I mean, of course, then you see that the difficulty increasing somehow. Now you know already things, but then you have an extra thing. And not only you have to solve an equation, but you want everything to be compatible. So maybe, why not?
Yeah, I was thinking maybe the space itself should be like your H times
cross something, yes,
yeah,
of course. It's not just H, it's going to be a product.
Yeah, so I was thinking maybe the functional is not too difficult to generalize to that situation.
No, this I don't think, but then the thing to maybe difficult to generalize is going to be these uniform a priori estimates, these kind of things, to get weak existence of these guys, you know, what the right energy class would be, in which class should we work. I mean, I'm not saying that it's impossible. I'm not saying that it's completely new. I mean, you have to start again, right? A lot of work for you guys. Here in this, for example, there is a moment map coming into the picture, because in general, what we ask, I mean, a moment map interpretation of this equation in here, this, as in the CSCK world, let's say. This I'm not sure, maybe, but it would be formal.
Yeah,
yeah,
that's fine.
It would be formal. I think I never write it down. So that because also in this, behind this, there is a polytope, but then you have to take care of the two things. I mean, because then I was very sketchy, but these two functions, so that there is a moment map in here. And these two weights are defined on the polytope. Okay. So when so this is actually the weight evaluated on the moment map associated to omega phi. So there is also this thing that is moving, and this is why the estimates are crazy. But then your question is another thing. It's like one level up, because you want to receive this equation as a moment map equation. So I'm confident, but I never wrote it down. So the answer is that I don't know.
Okay. Thanks. Well, I think my questions were answering your questions, so that's
very good.
Very good. People are very clever with their questions. If there is nothing else, I think we can thank Eleanora again for this wonderful talk.
Thanks to you.
Thank you very much. And the next colloquiums of the series will be in January. I think the next one is in Carlos III on the 16th of January. Okay, so see you there.